Hi everyone, this is Big Face from Big Face Robotics. Since the last video on my robot head build, I've made a few changes to the robot head. I think I discussed in one of the videos the fact that the sonar sensor was not overly reliable in this application, so I've made a few changes. The main one being removing the sonar sensor and replacing it instead with a accelerometer. It's an MPU 6050 accelerometer unit, and from it I can get roll, pitch and yaw values. So I've interfaced the accelerometer unit to the Arduino Nano, and I'm using the library from Jeff Roberg. I'll put a link in the description to this. It's very useful. It allows you just to grab the roll, pitch and yaw values straight from the unit and use them in your code. So with the accelerometer on the robot and working, I set myself a little challenge. I wanted to go away from the user interface that I was working on and set myself a little coding challenge to visualize the position of the robot head and do something a bit more unique with the servo position control. I've always been interested in neural networks. I've used them in the past, and I've also looked into population coding of neurons, so not using a single neuron to represent a value, but a population of neurons, where each neuron represents a unique value or position or whatever it might be. So I decided to start by looking at the yaw and pitch values coming from the accelerometer and plot them across a population of neurons in such a way that each neuron represented a position or a probability of a position of the robot head. I looked into head direction cells that are present in the brain, and this seems to work in a similar sort of way. So I was trying to replicate that. I've got some screen captures here of early work on this, and essentially I was taking the position values and converting that to a Gaussian distribution across a series of neurons, maybe somewhere between 50, maybe a couple of hundred neurons, and each neuron would be firing in proportion to where the head is positioned, at what angle it is. With the peak of the Gaussian curve being at the preferred firing direction of that neuron. And as you can see, as the head moves around, the firing pattern across the neurons moves around as well. I actually programmed this to wrap around at the end of the array of neurons, if you like, so that it was more a circular pattern. So the 360 degrees of rotation are represented by, or continuously by a series of neurons. So once that was working, I wanted to do something a bit more interesting and actually convert the two neural patterns from the yaw and pitch values into a two-dimensional neural sheet, if you like, where the pattern on there is almost like a hill of activity, the peak of which represents the yaw and pitch position of the robot head at the time. So I did that, and I'm using NumPy, so combining and adding and multiplying the matrices wasn't too difficult, and I'm using OpenCV to actually just display the array, the 2D array, in an OpenCV window. And it's quite nice because you can show it in grayscale, which is very simple. You can colorize the array and make it look a bit more interesting. So you can see on the screen the 2D array on the left, and that's a combination of the two 1D arrays representing the yaw and pitch values. And on the right I've got a matplotlib of the two Gaussian curves as they're moving around as I'm moving the robot head. And they're the two bits of data, if you like, that are combining to give the 2D array on the left. I've also got a colorized version, which I think looks a bit cooler, and you can see that moving around on the screen as the robot head is moved around. So that was a cool way to visualize the accelerometer data, and it is a neural network of sorts. It doesn't learn, but it does use population coding to represent the head position in a population of neurons. So I went one step further with that, and I wanted this neural pattern to actually control the position of the robot head. So the next step was to create a second 2D array that actually held the target head position, and that was constructed in the same way by combining two 1D arrays into a 2D array to give a hill of activity at the position that the head wanted to be. I then combined the actual and target arrays to give me a third array, and obviously that moved the peak of the activity away from the target, and it's essentially kind of calculating the difference between the two hills of activity. So by finding the peak activity within the combined array and comparing it to the peak activity of the actual array, I was able to calculate a difference to move the head towards the target position. And you can see that on the screen. The top left is the input, so that's the data from the accelerometer. The top right figure shows the target array, and the bottom left is showing the combination of the two. And you can see the little crosshairs in there moving around. And I'm then outputting a value to move the servos, which is the difference between the two peaks. And as that peak is further away from the target, the distance to move is more, and as the actual position reaches the target, the gap gets smaller, and acts almost like a PID controller, in that the movements are bigger when it's further away from the target position, and the position and the movements become smaller as it reaches the target. So that was a bit of fun. That was a little challenge to myself, and I'm happy that I got it working. I'm not sure how biologically plausible it is in terms of neural networks, and as I said, there's no learning in this. It's just a fun way to visualize and control the robot head, and I'm sure I'll build on some of this work in the future. So there we go. That's what I've been working on for the last couple of weeks, and I'll be back again soon with some more updates and possibly a new project quite soon. So keep an eye out for that. If you like my videos, hit the subscribe button, and thanks for watching.